if you want to share your screen when you're ready. Okay. Oh, it's a great pleasure to have Sergei Gukov join us from Caltech, early morning in Caltech. Sergei is going to, I forget the title of your talk. I didn't put it in front of me, Sergei.
It's from Ramanujan to Rokhlin by quantum states, I believe.
Ah, yes, excellent. Okay, so Sergei needs very little introduction, so I'm going to hand over to you immediately, Sergei, and you can begin.
Yeah, thank you.
Don't mind
so
if we
much,
ask questions as you go.
Yeah, actually, I was going to ask, how do you want to handle this? Is it okay to get questions in the progress of the talk?
I think it's okay if you don't mind. We're a small enough group that we've been able to manage to run it almost like an ordinary seminar where people interrupt. People can unmute themselves.
Fantastic, fantastic. Then just yeah, interrupt me at any time, or if there are questions in the chat, then feel free to let me know, and I'll try to answer them. I don't think I'll be able to see chat, but just ask. Yeah. Okay, so thank you very much for this opportunity. It's a pleasure. Of course, I wish I could do it in person, but hopefully next time. In the meantime, I hope everyone is doing well in this difficult times. So this first slide perhaps needs no introduction. What's shown here is, of course, harmonic oscillator, namely the simplest quantum system. Its energy levels, which are integer spaced, so the spacing between each level is integer number. The only interesting thing about harmonic oscillator, perhaps from this standpoint, is that it has ground state energy, which is not 0, but 1/2. And then everything is basically half plus an integer as far as energies go. Because energy levels are discrete, it's possible we can consider various quantities, ways to encode this information. So one of these things is to take a generating series where you take variable q, which is basically exponential of inverse temperature to the energy level, and form the sum. So each term in the sum corresponds to a particular quantum state. And this is 1/2 as a prefactor, showing the ground energy, ground state energy, and then you have 1 plus q squared, q cubed, and so on, basically encoding the spectrum of quantum harmonic oscillator. So as one wise man said, the career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction or complexity. And I think this applies very well to this talk today, because what I'll be telling you comes from quantum systems, in fact, from quantum mechanical problems, very much like harmonic oscillator. And what I'll be describing directly or indirectly is precisely the spectrum of such quantum mechanical systems. So we'll see functions like the one I showed on the previous slide a lot. In fact, here is in the bottom of this slide another example of a function, which is Q series. And just as in the case of harmonic oscillator, here the exponents encode various energy levels, and coefficients tell us how many of these levels we encounter. In the case of harmonic oscillator, there was only one energy level with a given value of En. In this example, something more interesting happens. There are many of them. In fact, they can be bosonic or fermionic. That's why you see plus or minus signs. Again, there is overall coefficient q to the minus 1/2, which means that ground state energy in this case is below 0, also by 1/2, kind of very much like a harmonic oscillator. And it is examples like this that we'll see a lot. And what I'll be telling you is precisely, as Sidney Coleman said, abstract versions or modified versions or variants of harmonic oscillator. They genuinely come from quantum mechanical systems. So this is actually a good way to think about what we'll see later on today. So in this quantum mechanical systems, the energy levels or the states actually have a nice geometric or quantum field theoretic interpretation. So they can be understood as counting various objects which minimize something, minimize some sort of functional. So good examples of such extremization problems are minimal curves. So imagine a soap film and it tries to minimize the area. So there are problems like this. In soliton physics, we usually minimize some sort of energy functional with a given topological charge or boundary conditions that leads to very similar problems in gauge theory where you count solutions to partial differential equations. And quantum mechanical problems that I'll be describing today actually are precisely of the sort where the coefficients of this generating series, or you could say the energy levels of a quantum system, can be interpreted as such solutions or solitons or minimal curves if you introduce some higher dimensions. So this kind of quantum states usually have a special name. They're named after Bogomolny, Prozert, and Sommerfeld, so people call them BPS states. These are particular versions of quantum states which satisfy these extremality conditions like minimal area surfaces or solutions to PDEs and so on. So these are the most cheerful pictures of Sommerfeld and Bogomolny that I could find. Actually, unfortunately, I couldn't find any picture, any photo of Prasad. I could trace his career path. So he started off early enough at MIT, then moved to LBL Berkeley, and then somehow I lost track of what happened to him. But ironically, or unfortunately, there is no picture. So if you have any photo of Prasad, it would be nice to fill in the gap. Meanwhile, these BPS states are heavily used in string theory, in quantum field theory, and another way to think about what I'll describe for you today is we'll be studying BPS states in certain high dimensional systems. Nevertheless, what I'll try to do today is to give you a very gentle introduction to the subject. So I'll not use any string theory, I'll not use any quantum field theory dualities or anything like that. It will be completely self-contained. So my goal is to give you ready to use easy guide to, first of all, computing this kind of partition functions, which count energy levels of quantum systems without directly describing the quantum physics behind it. So it will be more of a mathematical physics style seminar where I'll try to put equal focus or maybe even more focus on mathematical physics aspects rather than string theory or theoretical physics, which is under the hood in some sense. So the first part or main part of the talk will be introductory, self-contained. The only quantum field theory that you'll see will be two-dimensional quantum field theory, so nothing really advanced. And then toward the end, I'll tell you a little bit about some new results based on work which is still in progress that hasn't appeared yet, but hopefully will appear soon. So this work that I'll be presenting is based on a series of joint papers with theoretical physicists and mathematicians. So Dupay is currently at Harvard. Pavel Butrov is my colleague in Italy. You all probably know Kumar and Buffa very well. And Ciprian Manolescu is a mathematician, pure mathematician here in California. So that's what I'll be describing. When Brian Greene gave a colloquium more than 20 years ago, he started off, it was a math colloquium, so he probably wanted to be formal. So he started off with a definition because mathematicians like to have definitions, theorems, proofs, and so on. So he said a conformal field theory is a table of integrals. And I think I know what conformal field theory means. So it took me couple of minutes to process what he really meant by this definition. I'm not sure I fully agree with this, but all I can say is that this definition really applies well to what will happen today. So at least in the first part of the talk, I'll give you lots of integrals. So this will be ordinary normal integrals. It's something we learn in our undergraduate classes. So like I said, the level, I'll try to keep the level fairly accessible, at least for most of the talk. So we'll be using basically calculus or staying at the level of calculus. So trying to make it fairly elementary. You'll see there is nothing really fancy here. And we'll consider lots of integrals. So this again will be kind of advanced exercise in calculus. And all these integrals will be associated to graphs. So given a graph, you can think of it as an analog of Feynman diagram or some arrangement of spins on a lattice. We'll associate to every such graph an integral. And the graph consists of the following data. We'll need to know, of course, vertices of the graph, edges, namely which vertices are connected. It doesn't have to be a tree, even though here on the picture I show a graph with no loops, so it looks like a tree. And there is one extra detail that the graph will be decorated. So in other words, every vertex of the graph will be assigned an integer. So there will be this function a that assigns integers to vertices. In this case, this graph has 9 vertices. So there are 9 integers you can choose at random. They could be your PIN code for ATM card or something like that, assigned to each vertex of the graph. But of course, you can choose any other graph, thinking diagram of E8 or connectivity graph of the social network. And clearly there are as many graphs, especially with decorations by integers, as stars in the sky or fish in the sea. So it immediately opens territory for infinitely many examples. So then to...
Sorry, are they finite or infinite? Because you say Z, right? So, but probably you don't use all the Z, right? It's...
well, there are infinitely many such graphs. So here what I mean is that for each specific choice, so each integral, each problem, we kind of think about it as a homework exercise that we're going to do, will consist of taking a graph like this and selection of integers on every vertex. So we're not summing over these integers, we're just picking a choice. So for example,
No, I meant that is it finite? Like one graph you take, it's like finite number of vertices.
Oh yes, yes. We'll take each graph will be finite number of vertices. Yeah, thank you.
This was the question, very simple-minded.
Yes. Thank you. So the integrals that we'll do will be indeed kind of similar to what we do in statistical physics or in calculation of Feynman diagrams. If a given, say, Feynman diagram, then we also have vertices, edges are becoming propagators, so they're basic building blocks, and then we have to do certain integral. So here there will be something very similar, that to every vertex of the graph will associate an integration variable. So in this case, there are 9 vertices. There will be 9 variables to integrate over, so it will be a multiple integral, 9-tuple integral in this case. So yes, it's actually not typical problem we do in calculus class, but it's still reasonably well defined. And then to vertices and edges, we'll associate some universal building blocks. So again, think about them as, say, Boltzmann weights, if you think about this graph as a statistical model, or vertices and propagators, if you think about it as analog of Feynman diagram. The only other piece of data I need to introduce before I show you or we discuss the integrals themselves is this matrix with elements Qij. So this matrix is basically adjacency matrix of the graph. it has i's and j's running over the set of vertices. So it's, in this case, will be 9 by 9 matrix. So in general, it's size of the graph, basically. And element ij of this matrix is 0 if vertices I and j are not connected. It's 1 if they are connected, assuming that there are no repeated edges. So let's make this assumption for simplicity. And then naturally, this matrix is a little bit confused at position where I equals j, because what does it mean for vertex to be connected to itself? But notice that we already have a perfect candidate to put on a diagonal of this matrix. Namely, we have this integer labels at each vertex, a1, a2, and so on. So we can just put it on a diagonal. So this becomes well-defined adjacency matrix for this graph. And now here is the set of, if you wish, Feynman rules or Boltzmann weights. To each vertex decorated by this integer number a, we'll associate this factor. So x here is this integration variable of a particular vertex. Remember that each vertex gets a variable x that we'll be integrating over. Edge connects two vertices, so in principle it can depend on two variables, x1 and x2, or xi and xj, from each vertex of incidence. So here is x1, x2 appearing explicitly in this Boltzmann weight. And then the idea is very simple. So for every vertex, you put the factor on top in the integrand. For every edge, you put this factor and multiply all over all edges and vertices. And then you integrate over all these variables, x1, x2, and so on. The number of these variables, complex variables, is as many as vertices in a graph. And integration contour is unit circle for each of the complex variables. So there is an extra ingredient here in the end. That's a theta function associated with the quadratic form. Notice that adjacency matrix defined on the previous slide defines a quadratic form precisely on the lattice of same rank as number of x's. So we can just choose theta function. I'll give you explicit form on the next slide, but it is what you think it is. There is nothing mysterious about it. So we take product of theta function with these weights, and we get an answer. So the answer is actually going to be function of q, which enters the weights. So it appears here explicitly where the vertex shows up in the weight of the vertex, and it also enters the theta function. So the answer will be not a number. If there was no q dependence, it would be just numbers such as 2, 2.5, and so on, because variables x get integrated, they disappear. But in this case, we have dependence on this additional parameter q. At this point, q is just a parameter. So this kind of Feynman integral calculation or partition function will depend on q in the end. So at this point, you can naturally ask me, Sergei, why did you choose this very strange weights? So why this and not something else? It looks very ad hoc. Why do you? But here is another way to rewrite this integral. Here I condensed everything, all the contributions of vertices and edges. You can rewrite it in a more compact form. And here is this theta function. It's basically summed over lattice with the quadratic form q. So there is nothing surprising here. Perhaps the only point I should mention is that theta functions have characteristics. So if determinant of this matrix q is not equal to 1, then there are several choices of theta functions that we can have. There is not just one theta function, there are several of them, and they're labeled by cokernel of this matrix. So it's basically a set of z to the number of vertices divided by q times the number of vertices.
Sergei, one question. Is your q positive definite?
Yeah, that's a very good question. Thank you for asking this. In fact, as you can see, at this point, it's actually convenient for this theta function to be a nicer theta function to have some sort of definiteness. I think in this slides, I'm assuming that it's negative definite. So if Q is negative definite, it means there are more, or all eigenvalues are negative, and you'll see that with this minus sign in my definition, this will be of the form positive number times n squared. So it will be having Q powers going one way. Yeah, that's an excellent question. So let's assume that it's definite for now.
I don't understand you get several powers of Q, because you only get a power of Q for each vertex, and the number of vertices is fixed. So you get just one power of Q.
Not quite. So Q enters this vertex factor, and then what you said is absolutely correct. We just multiply them out, so you get one factor. But Q also enters the theta function. So this whole integral is a convolution of rational function, which depends on x's, doesn't depend on Q, and a theta function that does depend on both x and Q. So roughly speaking, what this integral does, it's trying to find in this product over positive, negative powers of x, which enter here, and theta function, tries to find term with x to the 0, because that's what this dx over x does. It basically picks out x to the 0 type terms. But because of the sum and expanding this rational function, it's not a priori clear what you're going to get. So that's exactly what we're going to explore. But yeah, that's a good question. Any other questions? In fact, I want to make sure that these are all very good questions. I want to make sure that at least this so far is clear, because I promised to give you a ready-to-use recipe to work with, or introduction to the story. And I want to make a point that this set of integrals are well-defined, indeed ready to use. So if there are any questions about the definition, I'll be glad to clarify it. Okay, so I'll take advantage of the technology and we'll try to share with you another screen. Here is a Mathematica notebook which does this integrals. So I promised you, or I claimed that these are well defined. You can work with them. So in particular, you can assign a student to compute this sort of integrals if they're indeed simple and well defined. And well, if you can assign a graduate student, probably you can assign Mathematica. So that's exactly what's happening here. This is a simple code that starts with the definition. It takes input data on the first page. Then it computes adjacency matrix, some basic data such as eigenvalues. Indeed, we discussed that it's better to have definiteness, at least for now, for simplicity. And then it actually starts to go in through the integral computation and spits out the answer. So let me make sure that I run it in front of your eyes. So here is a graph with 4 vertices. They're labeled by numbers -2, -1, -3, -7. So you see lots of mostly negative. That's why definiteness hopefully will show up. So I'll ask Mathematica to evaluate this notebook, and indeed it finished the calculation. So that's the answer that it spits out. Very much like what we saw in the beginning of the talk. For harmonic oscillator, it starts with Q to the half. This is ground state energy, and then it has the entire Q series, which shows us energy levels of this quantum mechanical system computed through these integrals. So I'm going to save the answer and play with an integral. So I did copy and paste, so just to save it here. And I'm going to change the integral. So in particular, I'm going to change the number of vertices. So they'll add another vertex. We'll say that vertex number 4 will be connected to another vertex number 5. And here I have to introduce another integer label, let's say 1. So let's change this to something else, let's say 8. And now I got myself completely new graph. So I added another vertex that now has 5 vertices and they are decorated by integers. So I can ask Mathematica to forget everything that happened a minute ago and redo the calculation. So that's another completely different Feynman graph or statistical model whose partition function we're evaluating. So let's see. First, before showing you the answer, here is, again, this initial part of the Mathematica code. You can see the graph. It now has 5 vertices, completely different graph. It's still negative definite, so we shouldn't expect any interesting things or surprises. Here we go, the computation. And if you look a little closer, I'm not sure how well you can see it on the screen, you notice that the answer here is exactly the same as what we had a moment ago. So we learned first thing, our first interesting fact about these integrals, that not always they give a different answer for different graphs. So in other words, that these integrals produce, that they group graphs into some sort of equivalence relations, where sometimes 2 different graphs give the same result. So in this case, we had one graph with 4 vertices, another graph with 5 vertices, and they gave exactly the same answer, the same Q series. So what is going on? So that's already first surprise.
Question. If you change these numbers 2, 3, 7, 5, this equivalence will still hold, or they'll be different answers?
If I take, so let me go back. If I take these numbers to be
different, yeah, like the last one, if it were not 1 but say 2.
I actually don't know, so let's try. So that's the beauty of it. So I'll ask Mathematica to forget everything. I already copied answer from the first calculation here, so I'm not going to repeat it again because this answer turned out to be the same. But let's do exactly what you suggested. So let's change the last one to be 2. So I don't know what will happen. So let's give it a shot. Okay, produce something. Aha. So yeah, first let's go back to this graph. So that's the graph you suggested. It is still negative definite, so there should be no surprises. But interesting thing that happened here, first of all, is that see, determinant of this matrix is no longer identity. The examples I chose earlier were such that determinant of Q was 1, so there was only one theta function, only one Q series. And in this modification, we get as many answers as determinant of Q. So apparently determinant of Q is 3, and probably this is written. Yeah, that's what it says here. So yeah, the answer is different, and moreover, even the number of such energy levels or spectra changed. So,
could I ask? Should we be surprised that the coefficients of the Qs are all integer? The ones you're showing are all integer. Is that obvious from just general principles without doing Mathematica? The coefficients of the Qs.
Yeah, that's a very good question. It's obvious from physics definition, which is again under the hood, because we're counting something. So we're counting energy levels in a quantum mechanical system. But purely from the integral definition, which I'll put back here, I'll come back to the presentation, you can actually, with a little bit of work, it's not as obvious as from physics, but you can still see that this convolution of theta function with a rational function always will give you integer coefficients.
Okay, so that's a general, you don't have to know physics to do that, just general fact.
Exactly.
Right?
Yeah.
Okay.
It's good to know physics because it's good to know that they're counting some energy levels.
Yeah.
But you're absolutely right that it's a simple theorem, well, a modest theorem that this always will have integer coefficients, but it's a theorem.
So it's like what Hardy and Ramanujan do when they wanted to count partitions and that kind of thing, right?
Exactly. So I'm glad you're already anticipating something like that, because it's all it's of the same type, roughly speaking, and we'll see more of it in a second. So what we accidentally discovered by playing with this integrals, so we were just in a sandbox, we were given some definition of the integrals, and we were exploring their structure without any prior knowledge or prejudice. And what we found is that they have some equivalence relations, that certain graphs produce the same answer. So in fact, these are the same equivalence relations that you would typically encounter in a textbook on Kirby calculus. So if you open this book, I actually have it in my office, you would find pictures like this, which express certain equivalences. I'll come back to this in a second. And one of these equivalences is precisely what we just did. It says that you can take any vertex of the graph, add another vertex connected to it with label ±1, and if you change the label of original vertex accordingly, you should get an equivalence relation. So that's an easy way to learn about Kirby calculus from usual calculus or doing this integrals. In fact, this is probably the fastest way to learn about Kirby calculus. So what is going on, and why this graphs have anything to do with Kirby calculus? This has to do with the following theorem, which is due to Licorice and Wallace, which says that every three-dimensional manifold can be obtained by cutting and gluing construction. If you have a knot or a link in a three-sphere and excavate its tubular neighborhood and then reglue back with a twist, then you can produce in this way any three manifold you want. So here is an example of a simple knot. In this case, the surgery coefficient that expresses how exactly you glue it back is a rational number. It's 4/17. In general, it can be anything, but the theorem says that you don't even need to use rational coefficients. You can always get away with integer coefficients and still cover all possible three manifolds in the world. So that's a useful theorem. And in this construction, there are certain equivalences. So you're allowed to replace one knot or link with one decoration by another knot on link with another decoration. And these are known as Kirby moves. So that's why I enter or put the name Kirby into this theorem. Now, what does it have to do with graphs? Imagine that you,
Sergei, is this statement something very simple in Chern-Simons' description of three manifold invariants? Or?
Sorry, say again, what's simple?
The statement, the theorem that you had on previous slide.
Well, Chern-Simons is a way to compute invariant of a three manifold. And of course, one can ask what happens in every invariant of three manifolds. You can ask how would it behave under this separation. But this theorem is actually just about groundwork in some sense. It's telling us what is the set on which we're trying to compute our invariants or partition functions. So it's just telling you how rich is the territory of three manifolds. So Chern-Simons is a way to compute their invariants, but it won't tell us how to construct three manifolds. For example, Donaldson invariants compute something over four manifold, but they don't tell us how many exotic four spheres we have. So this is more about construction of a manifold. So what does it have to do with the graph? So imagine that you have a link which is made entirely of unknots, these unknotted circles. And then these coefficients, A1, A2, and so on, are precisely the integer surgery coefficients, just like the theorem requires. So then basically you can express this data in terms of a graph. And that's exactly the graph I was showing you before. Namely, every time you have an unlink, this copy of unknot, you associate with the vertex. Every time the two guys are linked, as in a Hopf-link, you draw an edge, and so on. So basically, that's where the graphs came from. And what we saw in practice in this simple mathematical playbook is that doing certain manipulations on the graph, or equivalently on this so-called Kirby diagram, you get the same manifold in the end. So the statement of this theorem is that you have a way to construct something, namely you take all possible Kirby diagrams or such graphs, and there are some equivalence relations which don't change the answer, namely 3 manifold is always going to be the same. So in order to cover all 3 manifolds, so basically what we saw therefore is an invariant of a 3 manifold, because to construct invariant, what do you have to do? You have to show that it's defined on your construction of a 3 manifold. And then you have to show that it's invariant under certain changes that don't change the manifold. For example, in the case of knots, it would be constructing not invariant and then showing it's invariant under Reidemeister moves. In this world of 3 manifolds, you construct invariant, just like we did, and show that it's invariant under Kirby moves. And that's exactly what we saw. So we already learned something useful, that we learned that these particular integrals, and that's where it was important to choose rather specific weights that we assign to vertices and edges, are actually invariant with respect to Kirby moves. So if I made some random other choices, they wouldn't have this nice property, but with these particular choices, they are invariant under Kirby moves.
So, Sergei, can you explain what the Kirby moves are doing in the 3 manifold? Just perhaps.
Oh no, that I definitely would want to sweep under the rug, because in fact I would like to say that it's in this textbook the Kirby moves appear on page 300, and that I wasn't really joking when I said this is the quickest way to learn about Kirby moves, because here we can just play with integrals and see that they're invariant under this operations on graphs. And this is good enough definition for the purpose of this talk. So in fact, Kirby moves are exactly operations on this graph, shown here, but how they appear or how they rise and generalize to this Kirby diagrams takes quite a bit of groundwork, which definitely goes beyond this talk. So I apologize, I'll skip this. So this is too challenging for 1 hour talk, but yeah, for purpose of this talk, they're just operations on a graph. Yeah. Okay. So the only other thing I had to do is if we want to define it for general 3 manifold, we of course cannot do it with only this knots linked in a chain. We have to allow more sophisticated knots added here, and the only thing that will change, for example, if I change this unknot to some other knot, it will modify part of the integrand that depends only on this integration variable x. So there is one x for each component, and depending on this variable x, there will be slightly different integrand. So this can be done, and in the end, you can actually define this invariant, this integral for any 3 manifold. So here is an example.
The graph as well?
Huh?
Do you add more vertices to accommodate this larger knot, or you just say, no, it's just the weight on this kind of circle?
It's, yeah, so once you start adding these knots, what happens is that these vertices will know, this representation in terms of graph will no longer be accurate. Because here, if vertices are representing a knot, they're all the same. So they're all equal, it's complete democracy. But if you modify this unknot to a non-trivial knot, then of course it means that this vertex, this 8th vertex in this graph will be changed. So it's no longer equality. So I think a representation from
add like more vertices that you get more cycles in a graph, right? And so you just say that it's a weight on this.
Sometimes actually it's possible, not for this knot, but for simpler knots, it's possible to undo this operation. Again, it's about using Kirby moves to replace a complicated knot with a bunch of additional vertices. But it's not possible in general. For example, for this knot, it wouldn't be the case. So,
can I ask a question? What happens with non-orientable manifolds?
Non-orientable manifolds.
Closed 3. three manifolds which are not orientable? Prime manifolds.
That's fine. There are included in this construction. So far there is nothing really special about them, but they are included. So you can get them as well by this cutting and gluing construction. Yeah.
No, but these invariants, are they still valid? The manifold
Yes.
Okay.
So here is the result of, now you can start computing this invariance and much greater generality basically for any three manifold or any such cutting and gluing construction. You can compute them. So example on top tells you that you can start with one knot, compute this invariant. In fact, in this case, you can construct the same manifold starting with a different knot, and you can verify that you get the same answer. So it's going to be the same Q series, the same spectral function. Here is another example. This first one is exactly what we saw in the Mathematica notebook. So you can actually write it in a closed form as Q hypergeometric function. So the second one is hyperbolic manifold that cannot be represented by a graph. In fact, as I mentioned, this knot is the abstraction to doing this basically. And the answer you get in this case, and in many other cases, you can do it for any three manifold now, you're going to get a Q series which has Q expansion up to any order you wish. So here I show the term Q to the 500, and it has this coefficient. But I don't know what kind of Q series it is. So I cannot write it in a closed form. And these are sort of questions that we're going to explore next.
Just do you have control over the Hamiltonian that describes these systems?
That's why I sweep it under the rug. It's complicated. It comes from quantum field theory in dimension greater than 4. So it's a very interesting quantum mechanical system, which consists of taking high dimensional theories and putting it on three manifolds and additional spaces. So yes and no. It immediately takes us to higher matters. And in this talk, I want to stay.
No, that's okay. The question was if you've got control, if it's controlled, you have.
The Hamiltonian will depend on choice of a graph or choice of a knot, basically. And that's in some sense what this series encodes, but yeah, I would say no, not directly. Yeah.
Okay.
So it would be good to maybe have better control. So when we meet a friend for the first time, we want to know name, basic facts. Then we say, oh, I come from the same town, and we start sharing information. So think about this object that I just introduced to you as a new friend. So at first, we barely knew anything about this friend. We just knew that it can be defined using fairly simple integrals that you can give to a student. And there are lots of such integrals, just like Feynman diagrams. And then we suddenly learned first piece of information. We learned that these integrals actually have a meaning. From the topology point of view, they compute invariance of three manifolds because they're invariant under Kirby moves. And we just saw it with our own eyes. We saw that if we perform an operation of equivalence that's meaningful in topology, the answer doesn't change. We also know, but haven't discussed so far, the fact, so this is a question about dependence, how this answer depends on the choice of a graph or three manifold. It also depends on Q, this variable that was there from the start and produces a Q series. So it's natural to ask, how does it depend on Q? If I write Q as exponential of 2 pi I tau, is there any modularity inside, or is there something interesting about it? And then there is also dependence on this label B, which has to do with the fact that we get not only one Q series, but many of them, as many as determinant of this matrix. And from three manifold standpoint, this is actually the same as H1, or better yet, it's actually the same as set of spin C structures on a three manifold. So if you don't know what spin C structures are, don't worry, just think about them as dimension of first homology group. So if you're talking about Poincare sphere, there will be just one. If you're thinking about length space, then there will be several, and so on. If you have a torus, for example, free torus, there will be infinitely many such Q series. So therefore, what we have to discuss is dependence on Q and dependence on this additional label B. Let's start with Q dependence.
Sorry, I'm not familiar with the answer of this question. All three manifolds have spin C structure?
Yes. All three manifolds have both spin structure and spin C structure.
So the absence of it starts in 4 dimensions.
Yes, yes.
Okay.
In 4 dimensions, they may not have spin structure, but spin C structure always exists.
Not all
spin
4.
structure fails first in 5 dimensions for the
That's
manifold
right.
Q3 or SO3.
Exactly. Yes.
That is the first one.
Okay.
That's correct.
You know that you have always spin C.
Okay.
Yes, I'm glad to have some experts on spin C structures. Again, you can just think about them, these additional labels taking values in H1 if you prefer. Yeah. So speaking of Q dependence, this is a famous letter that Ramanujan wrote to Hardy. I'm extremely sorry for not writing you a single letter up to now. Unfortunately, this is how many of my emails start these days. Then Ramanujan says, I discovered very interesting functions recently, which I call mock theta functions. Unlike false theta functions studied by Professor Rogers, they enter into mathematics as beautifully as ordinary theta functions. I'm sending you with this letter some examples. So then he sent a couple of examples, well, about a dozen. And actually, the function that we saw in Mathematica, and that was one of my examples earlier, is precisely the one that Ramanujan wrote. So as far as Q dependence, it's interesting that these functions, at least one of them, and we'll talk about others, happens to be not modular in the sense of standard textbooks that have century-old history, but they're mock modular in this more interesting subtle sense that Ramanujan describes in this letter and in his examples. And this is a subject which is a very active area of research, this mock modularity. It basically says that it's not real modularity, but some kind of spoiled modularity. So this is not the only surprise about Q dependence. Can you guess what this is? This is percolation. When I look at this picture, it looks to me like white noise, and I always think of a famous painting. And depending on how you look at it, I guess we all see some different things in this painting. So percolation is a system which sure is in common certain feature with 2 other systems mentioned here. So listed here is a Q-state Potts model, which is a particular generalization of Ising model. It basically is Ising model where you have spins that take Q different possible values. So that was introduced by Potts in 1952. And you can think of percolation as a limit of the system where Q goes to 1. So naively, if you take Ising model and you only allow 1 value of spin, then it becomes kind of trivial. So here, central charge, C, that I'll talk about in a second, goes to 0. So you may think that there is nothing interesting. But actually, if you keep loop variables, then this is precisely the system that describes percolation in a critical regime. So another generalization of Ising model is ON model. This is basically a model where spin is allowed to rotate in n-dimensional space. And n equals 1 limit is when we get Ising, because O1 is basically +1 or -1 valued spins. But again, if you try to make model trivial, so to say, namely take n to 0, then what you get is self-avoiding random walks. And then here, I also mentioned quantum Hall plateau phase transitions. So all of these 3 statistical systems or models in StatMag share one common property. They all can be described by different logarithmic conformal field theories. So we all know that phase transitions, second order and similar phase transitions, typically are described by usual conformal field theories, such as rational CFTs. And logarithmic CFTs are kind of exotic beasts. They're logarithmic because correlation functions have logarithms, and they don't quite have nice modular transformation of characters. So logarithms of Q show up, and namely tau shows up in those transformations. So that's another way to think why they're called logarithmic. So they're typically non-unitary, may have zero central charge or negative central charge. And until recently, they were not really studied. But it's probably with work of John Cardy and others, they were made very famous, very popular. So John Cardy in 90 and early 90s advocated that percolation can be described by logarithmic, not the usual conformal field theory, but logarithmic conformal field theory, and made quite a few stunning predictions. For example, he predicted the exact formula for crossing probability from one side to the other. That's expressed in terms of 4-point function in a logarithmic CFT, and that has spectacular agreement with simulation. And what's shown here is analog of critical exponent. Here you can ask in percolation how many loops, that's of course a typo, with area greater than A you should expect. And the answer is number of such loops goes inversely with area. And there is a coefficient here, C, which is expected to be universal. And based on logarithmic CFT, Cardy predicted this number, and measured number is this. So that's definitely quite a success. So this basically made logarithmic conformal field theories very popular, and now they're studied. So it's actually interesting that when Cardy made this prediction, there were very few examples of logarithmic CFTs. We know from textbooks that there are many usual CFTs, unitary conformal field theories. There are WZW models, there are minimal models, and so on. At the time when Cardy was working on this or starting to work on this, there were basically only a handful of examples. They barely existed because people didn't want to look at logarithmic.
Excuse me, can you tell me what the C is again? I didn't catch what the C meant.
This capital C.
Yeah, capital C.
Yeah, so it's, if you ask how many loops in percolation you have with area greater than A, then such number of loops, of course, the greater the area, the smaller is the number, and the smaller is the likelihood to find them. So it goes inversely with area, and coefficient in the numerator is believed to be universal number. Yeah. So Cardy was basically predicting this universal number. Yeah. I think this, there is a great paper by Cardy with Robert Seif, who is now in Michigan, if I'm not mistaken. He's more of a material scientist, where they compare this predicted and measured, I guess. So now, if the subject is a little bit more popular, like mock modular forms, this is actually a hot topic, this logarithmic CFTs, and people try to construct more examples. So if you search for logarithmic CFT, you'll find some families of models which carry various names. For example, symplectic fermions. There is so-called triplet model labeled by integer p. There is a singlet model, which is actually a subsector of triplet model. That's why it has central charge. And here I give you a formulae for central charge. So you can see that for most values, the number is negative. So in fact, these theories are non-unitary because having logarithmic correlators is not okay in the unitary two-dimensional CFT. But again, these theories are very useful in physics. And natural question is, what do they have to do with our story, with the Q series? Well, the answer is also surprising. That same example I showed you earlier happens to be a character of 1, p singlet model from the previous slide with value of p equals 42. So when I presented this example at the conference last year in Bonn, Mike Friedman was in the audience, and when he saw the number 42, he said that, oh, that's the answer to the question about the meaning of life in the Hitchhiker's Guide to the Galaxy. So 42 here is not really special. It's amusing that it happened to be in this example, and since then I show it, but of course you can reproduce logarithmic CFTs of 1, p type for any value of p, so you can reproduce many other characters. And more importantly, in other examples, such as the second example I showed you before, where I cannot write this Q-series in a closed form, natural question is, what kind of function do you get? It is expected and believed that you get some kind of spoiled modularity of the mock type that Ramanujan was describing, or in terms of conformal field theory, we expect that you always get a character, perhaps of logarithmic algebra, but more generally maybe of general chiral algebra. And that's another interesting aspect to the story, that the friend that we encountered happens to be not just a random Q-series, it happens to be interesting Q-series from the perspective of Mr. Ramanujan. In particular, if this is really on the right track, this conjecture, then in conformal field theory, the basic information that describes characters is the scaling dimension. That's basically this ground state energy, this fractional power of Q that appears as overall factor. And natural question then is, does the scaling dimension have any meaning? What can we say something about the scaling dimension? So that's what I was planning to do next. And I wonder if I can have 5-10 minutes. I'm running a little late. Denjo, what's the time limit?
Yeah, no, we are not insisting on exact timing, and there are lots of questions, which is much more important to us that people follow.
Yeah, thank you. Yes, I appreciate it. In fact, are there any questions at this point?
If people have to leave, they can watch the video afterwards. So it's not really urgent. Okay.
Yeah. Right. So
in a supersymmetric case, do you have delta equals 0?
It's hard to say. This is directly related to Denjo's question from before, how much a priori we know about Hamiltonian of the system. It's effective quantum mechanics, and it's determined by choice of a graph or 3-manifold, and it's almost never supersymmetric. So, I mean, there are cases when delta is 0, but it's really hard to predict when this happens, and we don't know if it's going to be maybe, yeah, I should take it back. I think it's possible to predict when it will be supersymmetric. For example, for a 3-manifold, which is a circle cross Riemann surface, it will be supersymmetric. Yeah, that's a good question, indeed. Yeah, you can a priori predict when delta is actually 0. That's a good point. Yeah.
Can I ask a question?
Mm-hmm.
You are getting, you quoted the theorem of Lucretian about getting all 3 manifolds by surgery on knots. Okay, that's what you're. Now, the invariants you are writing down are all infinite series in Q. Okay? What is their relation to the knots on which you are doing the surgery, where you get polynomials in Q, like those of, I don't know, Jones and others. So they seem related, but not exactly. One is infinite, the other is.
Yeah, that's a very good question. I don't know the answer. In fact, that's a really good question to which it would be nice to know the answer. I don't know. You're pointing out one very important aspect, and that's how many practitioners working on this think about this Q-series invariants of 3 manifolds. They're basically analogs of John's polynomial, but not for knots, rather for 3 manifolds. But what's the direct connection? And if you construct 3 manifold out of knot, the way we did, that's not entirely known. In fact, obvious question, are they determined by John's polynomial or color John's polynomials? That's also not known. That's a good question. Very good question. So we talked a little bit about the meaning of this new friend in topology, we learned that it's invariant of manifolds. We talked a little bit about Q dependence, so I hope I intrigued you with the fact that you get interesting modular objects which are of modern interest rather than from textbooks. And now I'll talk a little bit, I'll spend last 5 minutes or so to describe the subtle question of dependence on class in H1, namely the fact that we don't get a single Q series, but we have several such things. Because this is also a little bit strange. Usually, when we get invariant of a 3-manifold, especially quantum invariant, we get just one thing. We don't get a package. So why would something be labeled by elements in H1 or spin C structures? That's a little strange. But there are actually such things. And to answer this question, and also to answer the question about what is the scaling dimension here, we turn to a subject whose founding fathers are Lev Pontryagin and René Thom. So they try to approach topology from a very interesting angle. So they define equivalence relation on manifolds, which says that two manifolds are considered to be equivalent or cobordant if there is a manifold of one dimension higher, such that these two manifolds can be realized as boundaries of the manifold of dimension +1. So this equivalence relation puts your d-dimensional manifolds in equivalence classes, and the set of equivalence classes is called cobordism group. So this is always a abelian group. And an interesting question is, what kind of structure can you capture with this abelian group? So here is a list of such cobordism groups for manifolds equipped with spin structure. This is probably the most popular example currently used in mathematical physics and theoretical physics and in pure topology. So classification of spin manifolds up to bordisms in dimension 1, 2, 3, and so on up to 9. So the reason it's used in theoretical physics is because recently, in order to classify exotic phases of matter, symmetry protected topological phases of matter, it was advocated that one can use spin bordism groups. For example, famous Kitaev's-Majorana chain in dimension 2 has two states which cannot be continuously connected without closing a gap. And these two versions of Kitaev's chain have to do with the fact that spin bordism group in dimension 2 is Z2. So there are two elements here. So we're interested in 3 manifolds. So natural next thing is to look at this bordism group in dimension 3. After all, I told you that so far my story had to do with 3 manifolds. And here the answer is trivial. So this bordism group is just 0. So it looks like the story is completely boring, but this is actually not quite the case, because the 0 here says that every 3 manifold can be realized as a boundary, namely it's cobordant to nothing, as a boundary of a 4 manifold, closed 4 manifold. And Rokhlin in 50s proved his famous theorem, which says that signature, namely the number of positive and negative eigenvalues of intersection form on a 4 manifold, is divisible by 16 if the manifold is spin. So in here we talk about spin manifolds. So therefore, it basically allows to define a very delicate invariant of a 3 manifold as a signature of 4 manifold that bounds it. Because of this property that signature of a closed 4 manifold is divisible by 16, this won't depend on the choice of 4 manifold, and you get invariant of 3 manifolds valued in Z mod 16. So this is called Rokhlin invariant. So another way to make the story in dimension 3 non-trivial is to ask for bordisms but satisfying additional conditions. For example, you can ask your manifold M3 to be homology sphere. So in that way, the corresponding Bordism group would be called homology Bordism group, would be roughly speaking measuring complexity of homology spheres. It would be telling you how many inequivalent classes you may have. And the definition of cobordism would be such that two manifolds would be cobordant if the manifold in one dimension higher is homologically a cylinder. So this homology Bordism group was believed for a long time to be, or not for a long time, for some time to be trivial. Just like this one, it could be just 0. But this is not the case. And actually, Rokhlin invariant is one tool that shows that its order is at least 2. So it cannot be trivial. This is the name for this integral homology Bordism group in dimension 3. So then people constructed very delicate invariants, such as Froishev invariant, which comes from gauge theory, which shows that this homology Bordism group is actually infinite. In fact, it has a Z summand. And then there are many more modern invariants, such as the ones constructed by Manolescu, who disproved triangulation conjecture, or famous correction terms of Oswald and Szabo, all of which provide invariants of these homology Bordisms. So these are delicate invariants which tell a lot about topology of 3 manifolds and 4 manifolds. And again, natural question is, why am I telling you about this? So what's the connection? It turns out that this Q series that I showed you actually has direct relation to 2 invariants on this slide. And in general, not just for homology spheres, but for general manifolds, Rokhlin invariance depends on the choice of spin structure. And this correction terms of Oswald and Szabo, they depend on choice of spin C structure. And remember that we also got something that depends on the structures. So in fact, the scaling dimension, this number, which is not integer, that appears as leading power of Q, is precisely the correction term of Oswald and Szabo. So this determines behavior of the Q series near Q equals 0, because when we write Q expansion, this ground state energy is basically the leading term. And likewise, you can find Rokhlin invariance if you go to the point Q equals I. So then you can get Rokhlin invariance of the same 3 manifold. So basically, this answers the question about what's the geometric meaning of this scaling dimensions, and also tells us that this Q series, which is set of invariants for a given 3 manifold, is actually quite powerful or delicate. In other words, it connects to this more subtle cobordism invariant. So I'll skip this slide and apologize for running over time, and thank you for listening.
Oh, let's thank Sergei for a fascinating talk and open the floor to questions. Bernard.
Yeah, thank you. Yeah, thank you, Sergei. When you talk about lock modularity, is that the kind of lock modularity described by Sanders or Sanders-Wiggers, or is it more general?
I mentioned 2 examples. This first example was literally from Ramanujan. So it's even more localized than Swagers, because Swagers developed the whole theory, but Ramanujan had a dozen of examples. So this one is literally one of his few examples. In the same way, you can reproduce, in fact, many other mock modular forms and false theta functions according to Swagers. So you're absolutely right that there is a theory and territory, but only very particular manifolds which seem to be ciphered reproduce or give answers in that territory. If we step outside of ciphered manifolds, such as this hyperbolic one, so this is a surgery on figure 8 knot, again, it gives a Q series which is definitely not Mach in the traditional sense, meaning according to Zweger's definition, and I don't know what it is. So it suggests that there is some sort of modularity in between what people call quantum modularity and Mach modularity. So where this thing would belong. So I don't know how to write this object in any closed form as, say, Q-Kuiper geometric function or num-sum to simplify the kind of understanding or get some insights into modularity. So I can't really say anything about it, but because we believe that it's a character of chiral algebra, it surely has some kind of modularity, but it may be character of logarithmic algebra.
Thank you.
Can I ask a question? From what I understand, the spin C structure depends on the metric, okay? Because the Clifford algebra changes as you change the metric. On the other hand, the manifold topology is independent of any metric. It is just a topological statement. Okay? So the issue I'm asking is, what is a merger? For example, the cobordance theorem, the things you wrote down, we know that Lorentzian cobordism between 2-3 manifolds does not exist. So I would like to know what is the relationship of all these considerations and the choice of the metric.
Yeah, that's a good question. So when people, and including myself, speak of spin C structures, they actually mean equivalence classes.
Yes, I know.
So we don't really mean, yeah, in a given class, one can choose a representative, which may depend on the metric and so on. But spin C structure can be thought of as a line bundle, and classes of line bundles are measured by first term class, C1, which takes values in H upper 2 of a 3 manifold, or by Poincare duality in H lower 1. So that's why I was saying that, in fact, it's probably not too far here, yeah, that you can think about this label B or spin C structure as living in H lower 1, or equivalently spin C, or equivalently H upper 2 of the manifold. So it's C1, first term class of the spin C structure that we usually talk about, or people talk about.
Yes, but these are related also to the Clifford algebras associated to. But the Clifford algebra is very sensitively dependent on the metric. Okay.
Yes. But the point is that Clifford algebra enters the definition of spin C structure, but a spin C structures as a set, they're measured by topological number which lives in this group, and it's independent on the metric, obviously.
Okay, I understand.
Sergei?
Yeah.
Did anyone discuss or found the relation between the Mach modular forms which appear here with those that appear in U-plane integrals for four-dimensional gauge theories?
Not as far as I know, but this is an excellent question. It has been asked a number of times. I think when Miranda Cheng, one of my number theory collaborators, gave a talk, she's more of an expert on this modularity. Greg Moore asks exactly this question, and probably in several other occasions. So that's a great question.
I think Jan Manschot is here. Maybe Jan Manschot knows the answer. No, he left probably. Because Jan was working on similar things with Greg too.
Right. Yeah, I personally believe there is a connection. I don't think it's being explored. So this is one of the roads not traveled yet, I think.
Because in those, in those cases for four-manifold U-plane integrals, there are lots of them that appear because you can change the group, you can change the four-dimensional theory. So each of them come with some. So for SE2, for example, it was a trivial case. It was the one that appears with Eisenstein series. But if you go to any other group and for any other four-dimensional theory and so on, this changes, and there are a bunch of them.
That's right, and
I'm sure you know this. I'm sure you know it. But when I look on this, I mean, one of those formulas just kind of, maybe that's the one.
I think that's a great question because it screams to make the connection, since in both cases the connection is between some modular type objects and topology. So it feels in the right territory to make.
Well, I mean, for me, the fascinating thing would be if four-dimensional topology and three-dimensional topology are connected by these modular forms. It would be very nice.
I totally agree. I can't agree more. Yes.
Could I ask a question about these mock modular forms? So I remember speaking to Victor Katz, and he was telling me that they're connected using some kind of supersymmetry, but I don't know whether that's related to what you're talking about at all.
It is actually directly related because Victor, in fact, he was one of the pioneers. So here I advertise this, where the logarithmic CFTs. So this is a list from, I think in this form, it was probably introduced only in after millennium. So this triplet was not really actively studied until 2000. But it's interesting that characters of some of these guys, such as singlet and symplectic fermions, appeared not under these names, but in classification that Victor was doing in mid-80s. So he has a couple of papers where he tried to classify vertex algebras, and luckily for us, or for modern developments, he didn't necessarily insist on unitarity. So he was okay to go beyond what physicists would tell him is legal, namely to negative central charge and so on. And in his table, actually some of the Ramanujan's expressions also appear. That's in one of the appendices in a famous paper from 1986. So for that particular thing, he didn't really need supersymmetry, but supersymmetry appeared in close cousins in next door examples. But he actually did stumble upon isolated elements in this family and logarithmic CFTs without thinking in these terms. So he just tried to classify representations and focus on just algebraic aspect of the story. But it's interesting and amazing to me that he managed to uncover some of the isolated examples, just like Ramanujan uncovered, say, 13 examples of mock modular forms or false theta functions. Victor Katz actually discovered logarithmic CFTs, at least some examples of them in his study. So
you mentioned Ising model as being Ising model. I don't associate with being a logarithmic CFT, but percolation certainly would be.
Yes, that's right. But here maybe I was a bit too quick. What I meant is that in all of these models, which are totally nice, for example, ON model with a general N, or Potts model where Q is less than 4, we start with a nice model and we do something illegal. We send it to limit where naively things would be trivial.
I see, yes.
But importantly, we keep the loop variables.
Yeah.
So it's not local anymore. So if you don't keep the loop variables, all of this would be trivial.
Well, even if Q is not integer, it's not unitary model anymore.
That's right. That's a good point. And actually, I don't know if it's an actual question then from our discussion is, can that be described as logarithmic CFT? So I don't know.
This reminds me. Oh, sorry, Arthur, go ahead.
No, I see Runcheng is here, and he talked yesterday about some non-unitary examples coming, well, those from the near group. And I wonder if their F functions are modular or modular.
Can you comment more on this? I'm not sure I have enough information to make the connection.
I see there's a visitor here, Runcheng Ren, but maybe he's not actually here.
Oh, I don't know.
He may not be. He may have tuned out for a minute.
Can I suggest something which is very, very probably just impression of this? That there are examples that we know in p-adic situation when you take p goes to 1. So, for example, you consider spherical functions in p-adics with p, and then you send the p to 1, and or I mean some Hall-Littwood polynomials which describe these spherical functions in p-adic. Then you send in special way p to 1, and suddenly you recover wave function of some integrable system, like the ones that Young studied with delta function potential, right? So these things happen, some magics, you know. I mean, you cannot take p goes to 1. I mean, it's just p is a prime number. But you take the formula and formally write that p is equal of exponential of epsilon and send epsilon to 0 formally. And suddenly you get from Hall-Littwood polynomial, you get solution that was found by Elliott-Lieb for this delta function interacting integrable system. So this kind of reminds something like that.
Yeah, that's very, very similar. I totally agree. Yeah.
And probably those McDonald's and Hall-Littwood polynomials and so on are somewhere behind of these percolation things. I would guess. But that's just very suggestions that happened in my life before with p goes to 1.
Right.
Might be happening again in my life from your lecture.
I know that in some of the, I'm not an expert on percolation, but in the case of self-avoiding random walks, there are some connections to fractals and chaotic dynamical systems such as sand pile models. In fact, there are many other chaotic phenomena in dynamical systems which have connection to logarithmic CFTs. And of course, fractals and those chaotic dynamical systems often are close cousins of something p-adic. So at least morally, there seems, and maybe even concretely, there could be connections. I don't know. That's, yeah. That's a good question.
Maybe it's difficult to explain like in 2 words, but if you can, like, what is the relation of the name? Maybe you can show some like easy dynamical system. I don't know, like golden ratio, whatever. Just easy example. Do you have some kind of nice picture?
Connected to this logarithmic CFTs?
But not necessarily, but just still like to the construction you were describing today.
Well, yeah, then it will be in connection with logarithmic CFTs.
Yeah.
Again, I don't think I'm not. I don't have it at my fingertips, so I would have to prepare. I didn't plan to speak on
no, you don't
systems.
have to, that's kind of an idea, whatever.
But I also want to point out that I don't think there is a general idea yet. So this is very emerging field. This logarithmic CFTs, like I say, when I was in graduate school, if I were mentioned logarithmic CFT, people would laugh at me because they would say, I mean, don't work on it. They are not unitary. Why do you want to study them? And actually, they were not popular. Like I say, in the 90s, when Cardy was making these predictions, there were not even examples of logarithmic CFTs. There were maybe just 1 or 2, like in Ramanujan style, but there were no families, no real theory at the time.
Bershadsky studied these things to some extent?
Bershadsky studied...
it actually was Gurari. It was in Princeton, it was Gurari.
Yes. Yeah.
And I remember when Gurari was studying, I think he was Polyakov student or something.
Yes.
Nobody wanted to listen to his lectures.
Exactly.
it was so sad to watch because he was really trying to classify them and so on. He was excited by Cardy, so was Zamaluchka and so on. But it was not even unpopular. It was advised not to get into.
Exactly, yes. Yeah. In fact, I remember I did encounter them in my grad studies, and I don't remember who, but somebody told me exactly this: don't waste your time, don't study, because they'll be never relevant for physics and so on. Which is strange because now they keep showing up. So to answer Alina's question, I think this is new frontier in the sense there is no theory yet. There are models, and we don't understand yet the principle. So I would love to take some chaotic dynamical system. My favorite is, for example, Chirikov's map, right? And say, oh, this is described by logarithmic CFT with p equals 42. But this paper has not been written yet. So,
well, random Schrodinger should be falls into this category. I mean, using the Efetov prescription, I think it's a C equals 0. It should be a logarithmic field theory. So anything random Schrodinger should fall in this category.
Fantastic. Yeah, that's a great candidate.
These are hyperbolic supersymmetric models, which are they certainly have central charge 0, and I suppose they must be logarithmically.
So we should write a paper on this then, if it hasn't been done.
I have one more question, which you showed this diagram where you found this point when you continued Q to I, right, where the Rokhlin came in, right? So does resurgence come into this to play here in an interesting way into this talk if you go further?
Absolutely, yes. So in fact, this is the slide that I skipped in the end because I was saying that in many examples, if you take generic free manifold, you can get the Q series and you write it to any order in Q that you like. So, but when we write something as a Q series, it's expansion near 0. So that's kind of by definition what we mean by power series.
Yeah.
So in order to say what happens at Q equals I, we have to extrapolate and have this jump. So that's actually where resurgence indeed comes in. So what I was showing on the next slide is in this example where I can generate as many terms as we want, but I don't really have control over modularity. Actually, modularity would be another way to tell me how to do modular transform from this region to this region. So that's, if we know, say, if it's mock modular or some other kind of modular, that would help. But in this case, we don't. And that's what I was showing on this slide, that numerics for resurgence is basically a way to answer such questions.
So what would it show? And what does it? What do you expect to see or hope to see from resurgence?
Well, resurgence to me is just a machine which is very effective in doing this extrapolations or analytic intuitions from one domain to another domain. So if I have a good control over expansion here, and as advertised, we can get, let's say, thousands of terms. So then answering a question of what function does in some other expansion region here, that's basically what resurgence does. It's a black box which takes expansion in one region and sends it to another in a kind of systematic way. So this is what's shown on this slide. It's a good example for resurgence. In fact, that's how it was done. This is the Q series. It has coefficients which are oscillating in sign. So it's plus, minus, plus, minus, plus, 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 then minus. For example, this is minus. But they're growing in absolute value. So the blue curve is the actual coefficients. So you see they're oscillating in sign. But the amplitude of these oscillations is growing factorially. So it's growing very fast.
Oh, that's how it usually goes, right?
Yeah.
Denjo, can I say one more thing?
Yes, of course, Samson.
Do we have time? Okay.
Yeah.
Sergei, what I got actually right now, suddenly it hit me from this lecture that good thing would be to study those scaling limits when the Virasoro or Kac-Moody characters actually give Dussler-Heckman integrals and recover the geometry. So you have the algebraic construction. Remember we talked about that some long time ago. And you take scaling limit, when it turns out that in that scaling limit, suddenly the manifold appears over which this is an integral, and it's a Dussler-Heckman type of integral. But I have never looked on logarithmic CFT characters. It would be a good thing to see what do you recover? Because in Vesumina, you obviously recover Kac-Moody orbit. When you look on Virasoro, you recover DFS1, right? So it would be good what these guys are giving now to have a look now.
I totally agree. I would love to pursue this. In fact, it's dangerous to make predictions about stock market or other things. But if I were to bet on the future, I would say that just like mock modularity is number theory version of this logarithmic CFTs hide a lot of interesting phenomena that we're just barely uncovering.
Right, but what manifold would you predict in this case? What manifold?
I don't. I would love to study it.
It looks like that it will not. This will not get to anything to Liouville, right? Because when you recover for Virasoro DFS1, you basically recover the universal Teichmüller space, and that's connected to Liouville. So
yeah, here it will be something different. Yeah, it will be
very different. So what would replace Liouville would be interesting. This is just a question for future maybe discussion. So sorry.
Yeah, I think that's a fantastic question, and there are many questions like this. In fact, question about connection to dynamical systems or the Effective model and so on are waiting to be discovered and published. Yeah. So
yes.
another question along these lines, which we probably should ask Werner, is so he studied connection between rational CFTs and K-theory via their massive integrable deformations. So another thing related to question you're asking, Samson, might be to study massive integrable deformations of logarithmic CFTs. And in Werner's case, K-theory class had to be trivial or torsion. So I would expect that here the corresponding K-theory class is non-trivial. And then question is it related to central charge of this logarithmic CFT, scaling dimensions? So again, maybe Werner
actually,
has some.
Unfortunately, Werner had to leave. So.
Since you brought up Werner, right? There was another thing that Werner, I mean, I hope he's still around here. There was another thing.
He isn't, Samson. He's gone.
Okay, well, it's pity, actually. But Werner, long ago, Werner and I had some beautiful discussions about Seiberg-Witten relation to this. See, he had somehow managed from Seiberg-Witten to get this rational two-dimensional rational conformal field theory, not characters, but something like dimensions or something like that. He was, I'm talking about almost 20 years ago. And that connection is still unclear to me. I don't know, Dejo probably remembers lectures that Werner gave long ago about Seiberg-Witten somehow connected to rational conformal field theories. So that might be related to the question I was asking, whether Donaldson theory mock modular forms are here appearing, because that's what enters in the prepotential for Seiberg-Witten. Anyway, so Werner had some nice observation. It is a pity that he's not here. He would immediately correct me.
Yeah, we should ask him, because I don't remember, to be honest, what was the connection to characters.
Oh, this was not published. I don't think he published that. It was just nice discussions at Trinity College that he was giving some lecture, and we then ended up discussing this, and then it kind of vanished somehow.
Yeah, then it's not surprising I don't know this, but sounds interesting and sounds quite relevant. Yes.
I'm still recording, so I should probably stop the recording at some point. Yeah, just before I go, before I finish, I was curious about the Rankine function. The Rankine function is Rankine invariant. Is it related to the Rankine function that crops up in dimer models, by any chance? You mentioned these sandpile models. It crops up. It's closely related. There's a Rankine function that crops up there. Are the Rankine invariants closely related to those by any chance?
No, I don't think.
It comes
well,
up
I mentioned a sandpile model in the context of Alina's question about connection to log CFTs, but I don't know if Rankine
comes
function
up in the
plays a role
amoeba.
there. Yeah, yeah.
Questions associated with the amoeba.
Right. Yeah, it controls basically the kind of limit shape behavior of the model, but I don't know. So here it will be analogous to taking limit q goes to 1, roughly speaking. So I would expect that if the answer is yes, we should expect that in the limit q goes to 1. So on this graph, it would be in this region, in the q plane. Again, that would be my guess just by relation between Rokhlin and limit shape.
Okay.
But I don't know. This is just expectation.
So when is this, do you have a paper out yet, or is it still a work in progress so we can look at this?
The main part of what I did today is published in those papers with Manolescu, Komorova, and so on. And this last part about relation to cobordism and variance hopefully will appear soon, maybe even next week if you're lucky.
Excellent.
Very good. Okay, well, thank you very much. I'm going to stop the recording because it's probably getting too long a recording at this point. Okay.
Thank you all for coming. And